Hello everyone. In this lecture we are going to discuss methods for visualizing hierarchical data. Hierarchical data are everywhere and therefore visualizing hierarchical data is of great importance and it has many applications. In terms of data analytics, hierarchical data visualization is used to display how certain items are ranked and ordered together in an organization or a system. In hierarchical data, each category can have subcategories, and subcategories can have sub-subcategories, and so on. We are specifically interested in hierarchical quantitative data. We have some hierarchically organized quantitative data, and we want to visualize them in an effective manner. Hierarchical quantitative data can come from a variety of sources, such as CPU usage, disk space usage, budget reports, stock market, etc. Our goal in this lecture is to introduce charts for visualizing quantitative hierarchical data. There are many charts for visualizing hierarchical quantitative data. Here I'm showing 6 of these chart types, namely tree maps, sunburst charts, icicle charts, nested circle packing or circular tree map, stack bar charts, and radial bar charts. Out of these 6 chart types, we want to focus on 3 of them, namely tree maps, sunburst charts, and icicle charts. A tree map is a visualization that displays hierarchical data as different groups of nested rectangles. Tree map gets its name from tree diagram or classical tree, which is similar to the trees that we use in computer science to show a hierarchy. Just like real trees, in tree maps we have the root, the branches, and finally we have the leaves. A sunburst chart uses concentric circles or rings to visualize hierarchical data. The naming is due to the appearance similar to the sun with rays issuing in all directions. And icicle charts use a series of stacked and contrasting rectangles to represent levels in a hierarchy. They are called icicle charts because they resemble a row of icicles hanging from, let's say, the edge of a roof. Like real icicles, icicle charts start big at the top and get smaller toward the end and point in the downward direction. Okay, you might say we can change the color of the charts and see the resemblance here and here. But there isn't a lot of resemblance between these two. My answer would be we need to look at the bird's eye view. Tree maps do look like forested areas in cities. For example, this picture is a good one. We see nested rectangles all covered with trees. And here I'm showing the nested rectangles creating kind of a hierarchy. New York Central Park is another example. I'm sure that we can imagine some nested rectangles here. Now, let's look at a very simple example with just 3 levels in the hierarchy. Here is the tree diagram or the classical tree of our hierarchical quantitative data. A is the root, B and C are the children, and C has 2 children, D and E. We have assigned quantitative values to each leaf, and for internal nodes such as C, the weight is the sum of the children's weight. So for C it's 50 and for A it is 100. Here is the tree map representation of our hierarchical data. It is pretty simple to follow because we have a simple hierarchy here. We have A, which has 2 children, and C, which has 2 children as well. The root node is represented by the large rectangle, which is this, and it contains the lower level rectangles within it, all the way to the base rectangles that represent the leaf nodes. The area of each rectangle is proportional to the quantitative value that it represents. And here is the sunburst representation of our hierarchical data. We have concentric circles, as you can see, forming rings, and each node is represented by a curved segment whose angle is proportional to the node's quantitative value. A here is the root, represented by a circle in the center. B and C are A's children. They have equal quantitative values and hence same angles, and they reside on the first ring. And C has 2 children, namely D and E, and they reside on the second ring. As you can see, each curved segment or wedge on an inner ring bears a hierarchical relationship to those segments of the outer ring that lie within the angular sweep of the parent segment. By looking at segments on each ring on sunburst charts, we human beings use a combination of the segment's arc length, angle, and area to perceive the value that the segment represents. And here is the icicle visualization of the hierarchical data. A is the root, B and C are the children placed under the root having the same width, and C has 2 children. They have the same values and therefore the same width. Pretty simple, even simpler than sunburst charts. As I said earlier, icicle charts are based on the visual metaphor of icicles. They are very similar to sunburst charts, except that they don't use a circular and polar layout. So instead of arc length, angle, and area of segments, they use width of rectangles to encode quantitative values. The biggest rectangle on the top represents the root node. The children nodes are placed under their parent node, and each node's width is determined by the sum of its children's width. Here I'm showing how an icicle chart is simply a sunburst chart transformed from polar coordinates to Cartesian coordinates. Polar coordinates to Cartesian coordinates. And here I'm showing screenshots of the original articles that first introduced these charts for hierarchical data visualization. Tree maps were introduced by Ben Schneiderman at the University of Maryland. Sunburst charts were introduced by John Stasko and Eugene Jiang at Georgia Tech. And icicle charts were invented by Kruskal and Landwehr. And Kruskal is the same Kruskal that developed the famous Kruskal algorithm to find a minimum spanning tree in a connected graph. At that time, they were affiliated with the Bell Labs. Tree maps came out in the 90s, sunburst charts came out in the 2000s, and icicle charts are the oldest ones. They came out in the 80s. Okay, let's stop here. We will go over an example of a data set and tree map, sunburst, and icicle visualizations of it in the next lecture. See you soon.